Okay, hi everyone, welcome back. So, we have learned about in previous session, we have learned about the formation of vacancy and equation for determine the equilibrium concentration of mono vacancy. Okay, these are the two important things we have learned, and today we are learning about die vacancy and its equation and the experimental determination of enthalpy of vacancy formation. Experimental determination of enthalpy of vacancy formation. Okay, so we will start with a vacancy cluster definition. Cluster means if more than one vacancy present present at a time and at a single position, then it is called vacancy cluster. Die vacancy. Now we are coming to the die vacancy concept. A pair of vacancy on adjacent atomic site adjacent atomic sites is known as a die vacancy. So that can be given by the this notation n of 2v equal to total number of pairs into the probability that the given pair is in a vacancy. Total number of the pairs, and we should need to consider the probability term. The probability that the given there is a die vacancy. Then we have 1 by 2 such n plus capital N plus NV into the probability is given with the help of equilibrium concentration of monovacancies. We have written the square, it should be at the adjacent. It should be and symbol should be there. That's why we are multiplying. Then this is taken this side, the LHS side. Then we can have x2v equal to 1 by 2 into z total number of the pairs into x1v whole square. It's purely statical equation. Statistically explained equation, ignoring the binding between the two vacancies. So afterwards we can tell so note number of the bonds broken for the divacancy is always less than the number of the bonds broken for the monovacancy. Number of bonds broken for divacancy is less than the number of bonds for two monovacancy. I will explain this one. See here one divacancy is there. So divacancy is present here. Okay. So here totally how many bonds are broken? So 1, 2, 3, 4, 5, 6. 6 bonds are broken. Whereas to create two separate mono vacancy, how many bonds should be broken? So 1, 2, 3, 4. 1, 2, 3, 4. That means 8 bonds are broken. That's why here for to create a one divacancy we need lesser enthalpy as compared to that of the two mono vacancies. Then we can write it as delta H 2V is less than 2 into delta H 1V. Correct? Then from this equation we can write it as delta H 2V is equals to 2 into delta H1V. We are considering the binding energy. Due to this binding energy is extra added for the H1V, binding energy of divacancy. So binding energy of divacancy. Okay. Then we know the previously from the previous slide we know the value for the delta H2 H2V equal to Z by 2 exponential of minus delta 2 H2 divided by KT. So we know the value for this equation. Then uh, we know from here from this equation we can substitute in this equation and we can get the concentration of two vacancies. That is H2V equal to Z by 2 exponential of B2 by KT exponential of minus 2 into delta H 1V divided by KT. Then finally we can write it as delta exponential of B2 so I will write it in the final expression will looks like B2 by KT X1V whole square. I will write it in a white screen so that it will be very useful for the analyzing the expression. x2v z by 2 exponential of b2 divided by kt, so x1v whole square. Okay, so one general question that can be asked in every interviews, even though the enthalpy of formation of the die vacancy is less as compared to the individual mono vacancy, that is delta H2V is less than 2 into delta H1V. So why the formation of die vacancy is less than that of the mono vacancy? This is the condition. Even though the enthalpy is less for the die vacancy, why the formation of die vacancy is less than mono vacancy. So what's the reason? Because of the configuration entropy for the die vacancy is less than that of the mono vacancy. That's why the formation of die vacancy is rare. Answer is based upon the configuration entropy for die vacancy is less than the mono vacancy. So due to this, die vacancies are forming the die vacancies very rare. That means this is in a mono vacancy only one single atom is substituting everywhere. But here the die vacancy, a pair of an atom has to be replaced with a pair of vacancy, which is very difficult. That is the configuration is less as compared to that of the mono vacancy. So one of the paper has given this. So graph is plotted with the log of x1v and log of x2v with 1 by T temperature. Then the slope is this is for x1v and this is for x2v. So consider at this temperature, this is for 1760 degrees Celsius and this is for 400 degrees Celsius. So everywhere the concentration of a die vacancy is less than that of the mono vacancy. This graph will confirms that the formation of die vacancy is very rare and very rare compared to that of the mono vacancy. But we can see the gap between these two. At lower temperature, the formation of die vacancy is very less as compared to the mono vacancy. And when we move towards a higher temperature, there is a gap is very less. That means the probability of finding the vacancies and increase the rate of probability of finding the vacancy is more than that of the rate of finding the mono vacancy. So conclusion that we can write it as vacancy concentration become concentration become significant only at very high temperature, close to melting temperature, close to melting temperature. This is the conclusion that we will get from the this graph. Now, in this lecture, we will move towards the experimental determination of enthalpy of vacancy. Experimental determination of enthalpy of vacancy formation. So, the basic equation is, we know that x1b equal to exponential of delta s 1b vibration to the k value into exponential of minus delta h1b divided by kt. So, there are totally in this video lecture we are covering totally four methods we are covering. First of all, differential dialometry, dialcometry, is DD. Second, residual resistivity, resistivity, positron annihilation. Okay, let's start with the first one. That is differential diameter. Heating a material with a from low temperature T naught to high temperature T naught. First of all, heating a material from T naught to T temperature. So I will explain some terms used in this method. V naught comma V is given by volume at T naught and T, volume at T naught and T, A naught comma A, lattice parameter at T naught and T, volume per site omega omega naught and omega, volume per lattice site and N is the number of lattice site, number of site comma N is given as extra vacancies at T, extra vacancy at T. Okay, we will start that change in the volume by heating the temperature due to change in temperature is given by V minus V naught. Then V can be written as N plus L into omega, capital N into omega naught. Then delta V can be given as N into omega minus omega naught plus small n into omega. Delta V is equals to N into delta omega plus N into omega. Change in volume per lattice site. This is delta omega can be given with the change in volume per lattice this is delta V for lattice side we have, and this is only due to the this change is due only for the thermal expansion. Then we will divide the initial volume on the both the side. Delta V by V naught equal to N into delta omega N into omega naught plus small n divided by capital N omega divided by omega naught. Then we know that n divided by n capital N equal to x1v. This is get cancels. Delta v by v naught equal to delta omega divided by omega naught plus x1v. This x1v can be written as x1v equal to delta v by v naught minus delta omega by omega naught. We know that delta v by v equal to 3 times that of change in length by original length, and delta omega divided by omega naught is equals to 3 into delta a by a naught. Okay, then substituting these two values in this equation, then x1v can be given as 3 into delta L by L naught minus delta A by A naught. This is the method from which we can calculate the vacancy conservation. So I have left a small part, that is we know that x1v equal to exponential of delta s 1v vibration divided by k exponential of minus delta h1v divided by kt. So this equation that we have derived from the in previous class, taking ln on both sides, ln of x1v equal to minus delta h1v divided by k 1 by t plus delta s 1v divided by k of vibration. So this is the equation that we have is y is equals to mx plus c4. Then c is this one, Okay, so I'll explain. Due to technical issue, I lost some of the things. I'll write it quickly. Flow, delta S1V vibration, exponential of minus delta H1B divided by KT ln of X1B equal to minus delta H1B divided by K 1 by T plus delta S1B divided by K. It is in the form of y is equals to mx plus c. Then the graph will be, it's having a negative slope with the y interception c. This is the slope as minus delta H1B divided by K. Okay, this is the y interception delta S1B divided by K ln of X1B versus 1 by T. K. This is the interpretation of this equation. Next is residual resistivity. Resistivity, resistivity. So I will write the definition here. Residual resistivity in a material, resistivity in a material is due to thermal vibration, of an atom atoms and due to its defects. Okay, then the total resistivity is given as rho equal to due to thermal, due to vacancy plus due to defects. Then from this equation, change in the resistivity is directly proportional to the change in its vacancy. Resistivity of the vacancy, which is directly proportional to vacancy concentration. So there are steps to measure change in resistivity. First step is measure rho naught at T naught. Eat a sample to temperature T. Quench it to temperature T naught to maintain the next step is measure the resistivity resistivity rho at T naught. Then we will have this delta rho is equals to A into delta x1b, then the delta rho is equals to A into exponential of delta s1b vibration divided by k value exponential minus delta h1b into kt. Similarly, by taking a line on both sides, we can plot a graph which is having a negative slope. Line into delta rho. The slope is delta h1b divided by k value. This is 1 by t value. Okay, these are things we obtained from the resistivity. Next is by the positron annihilation method, which is a last method. In this method, a piece of metal is kept close to the radioactive isotopes, and the commonly used isotope is sodium 22, and this will emit a gamma radius. And the basic funda in this positron annihilation is the vacancies are the where the position places are the electron deficient area, and these positrons, when we send the positrons to the this deficient electron deficient areas, they will take more time to neutralize. Okay, so this is the basic funda. So what are the steps that we are carrying out? First of all, a piece of a piece of metal is kept close to radioactive radioactive material, radioactive isotopes, commonly used is Na22, sodium 22. This will emit gamma plus positrons. As we know that vacancies are electron deficit area, the positron, hence positron will take more time in vacancy to annihilate. That means number of vacancies is directly proportional to life of lifetime of positrons. That means if there is a more number of the vacancies and it will takes more time to get annihilated and get neutralized. That's why from this time we can correlate to the number of vacancies. Okay, so this is all about the methods that been used to measure the concentration of vacancies. Okay, so next we are talking about the random walk theory, Einstein's smallest Chomsky equations, etc. Thank you.